So in this section, we're going to see all these weird kind of new players for our reactions. And these are reactions now of the nucleus. So instead of seeing like H plus or ammonium, these kind of things, we're going to see protons, neutrons, positrons, jazz like that, which is pretty crazy. One thing I forgot to mention, that if this is something that interests you and you want to stay in the state of Oregon, there's one place and one place only where you can study nuclear chemistry, and that's Reed College. And for whatever reason, Reed College, of all places, has a complete reactor, and they do a lot of this kind of stuff, which is just crazy. Here at Mount Hood, we have very primitive ways to detect some things, but Reed has the full thing. So anyway, if this is ever something that's interesting to you, Reed College is the place to go in Oregon. Of course, other states have different things too, but just FYI. Now I'm going to show a video here when it talks about alpha, beta, and gamma radiation. And when he's going to use what's called a Geiger counter, which is used to detect radiation. And listen carefully to the video, and you'll hear like pop, 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 pop. And that's the radiation being detected by the Geiger counter. And the more pops, the more radiation and stuff like that's going to happen. So, all right.
You're aware that radioactive materials give off energy, especially if we expose this sample to ultraviolet light. We can see it glow. There are three different types of radioactive particle energy. There's alpha radiation, beta radiation, and gamma radiation. Here we have a nuclear scaler that measures radioactive decay. Each click that you hear is a nucleus of an atom that is decaying by giving off a radioactive particle. This is a Geiger tube, and it has a window that allows the radioactive particles to pass and records them on the nuclear scaler. What we'd like to do in this demonstration is to test our samples both for penetration and also for the distance that you must be away to receive any protection. Let's place a beta particle in our sampler. We notice that there's a slight increase in the counts. The background radiation is not nearly that fast. Here we have some small sheets of lead that we'll place there to provide some screening. We notice that even one lead sheet dramatically cuts down on the beta radiation. 2 and even 3, and we're down now to quieting the counter back to background radiation. Let's see if that also works for gamma radiation. We'll change the sample. You notice immediately that more energy comes from the gamma. 1 sheet of lead and 2 and even 3 that quieted the beta does not quiet the gamma. We can add even a 4th. Gamma has the greatest penetration of all the radioactive particles, alpha and beta. Gamma is an electromagnetic energy wave. Well, let's see what happens as we go from being close to a radioactive source to far away. We notice that the amount of radioactivity is greatly decreased by distance.
So a couple of things about this admittedly dated video. First of all, even before we put any samples in the Geiger tube thing, there was still hits happening, all right? And we'll talk about that, but around us all the time, even right now, there's radiation, all right? It comes from solar events down to the Earth. It comes from internal Earth things up to us. There's all kinds of different man-made and artificial reasons why these things happen, but there's a little radiation around us all the time. Now, if radiation is a new thing to you, I don't want you going home and having sleepless nights over it, because our bodies have naturally adjusted to some radiation around us all the time, all right? And that's okay. So background radiation is not necessarily like a bad thing. Our bodies are used to a certain amount, and that's really important. However, these are dedicated radiation sources with alpha particles, beta particles, and gamma. Now, alpha would have been stopped pretty easily, but he started with a beta particle, and every time you heard that click, 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 that was something happening. So when he put the beta thing in the counter tube, there was definitely more clicks than there were when it was just the background. So beta was doing it, but beta was stopped pretty readily by lead. Right? Put some lead on it, and that kind of slowed that down. But crazy gamma, man, right? First of all, that was a super energetic source, but you can see how he put lots of lead on it, and it didn't really stop the counts that much, maybe a little bit, but not very much. If you get to a gamma source, I said earlier I would run if someone shot a gamma gun at me, because literally running is probably a good thing. The farther you are from it, then the gamma radiation is blocked by air particles and jazz like that. If you have a lot of lead, you can stop it, but usually it's better just to get away from it. It's pretty powerful kind of stuff. So, any questions on that?
Is he not like exposing himself, or is that not a big enough source to be an issue, or like?
Really good question. These little circular things are used in academia, that thing, and they basically are just one direction radiation sources.
Okay.
So 90+% of the radiation is going like straight up, that's right. Is there no radiation going left or down? No, there is some, but it's a lot less. And these are ones that we use, similar ones anyway, here at Mount Hood.
Is there a way that they can like I don't know how that would be like stored, for example.
Oh.
Like, what do they? Because if you were ever over it, you would be exposing yourself to it.
Great question. We have what we call the pig here at Mount Hood, and it's basically like a lead container, and with an inner diameter just big enough to store these crazy things. So we normally keep it in there so the radiation is blocked by the lead. We have like a cap for it, okay? And then when we're ready, we take them out, and yes, we are exposed when they're out and stuff, but it's pretty minimal time and stuff like that. And as you got more complicated sources, you could have like lead gloves and a lead shield. Like in the dentist's office, they make you put that shield thing on, you know, and they always say, oh yeah, it's totally safe, and then they run to the next room. But anyway, you could do something like that if you had like a more concentrated gamma source. Absolutely. Really cool question. So yeah. Other questions? Yeah, keep
What would be like an example of what cameras are used for?
Cool. In astronomy, gamma radiation is used to detect things that are happening like on other cycles of suns and stuff like that. So they can detect, and gamma radiation, as I understand, Kate, they can go back almost to the beginning of the Big Bang and like see like how things formed and stuff. That's just the first thing I can think of. Now I know that gamma radiation is used sometimes to see inside of things and of our bodies, and I believe, Caden, they use gamma radiation sometimes for killing cancer cells. And I'm not an expert in any of those things, but those would be some uses for it and stuff. So it's, just like a gun can be used for bad things and good things, right? It keeps you safe and other people won't invade your house, but on the other hand, Ukraine. So anyway, gamma radiation is the same thing. There's a lot of bad uses for it, totally, but in the right way, like I know in astronomy, now they've got lots of discoveries from using gamma ray detection and stuff, so good question. Other questions? Okay. Now, the first big thing we're going to do in this section is balance a nuclear reaction. And in Chem 221 on, we've been really involved with balancing a regular chemical reaction. And it's a similar process for a nuclear reaction. But in a nuclear reaction, the thing you want to think about is not so much the electrons, which we focused on the other ones. We're going to focus on reactant and product protons and reactant and product neutrons. And in a balanced nuclear chemical reaction, you've got to make sure that the protons are the same on both the reactant and product side, and you want to make sure that the neutrons are the same on both reactant and product side. That's kind of the punchline of balancing nuclear reactions. So here's an example of a balanced nuclear reaction. This is a radium. It's radium-226. That's how we would talk to each other about it. And radium-226 breaks down to radon, that's radon right there, radon-222, and an alpha particle. So radium-226 it breaks down through alpha decay, we'll talk about that, into a radon 222. But for right now, if you look at the lower left-hand numbers on the reactant and product side, as well as the mass numbers, the upper left numbers on the reactant product sides, they're the same. So radon is number 88 on the periodic table. That's the number of protons that we're starting with, reactive protons. And on the product side, we've got radon, which is 86 on the periodic table, and an alpha particle, which is 2. So 88 equals 2 plus 86. Woohoo! Reactant protons equal product protons. Now the top numbers are protons plus neutrons. But if you think about just as being an indicator as to number of neutrons, we want to make sure those numbers match as well. And sure enough, 226, the mass number for the radium, equals 4 plus 222, the alpha particle plus the radon. So this is what it means to have a balanced nuclear reaction. You just want to make sure all the left-hand numbers are balanced, reactant to product side, and you want to make sure the upper left-hand numbers are balanced, reactant to product side. If you do that, then you have a balanced nuclear reaction. Okay? We'll see examples of this here coming up. This is an alpha particle, once again. So people would usually say this undergoes alpha decay, or an alpha particle is lost, something like that. Emission is a word that's used sometimes. Okay. So here's an example of how this process works. Uranium-235 is one of the big sticking points when it comes to the Iran nuclear deals that they talk about sometimes in the news. Iran wants to use uranium for what they claim are peaceful purposes, all right? So making nuclear energy, stuff like that. A lot of the powers that be are worried that Iran would use uranium-235 for making nuclear weapons, which is probably not the best call either. Either way, this is why people are worrying about it. Uranium-235 decomposes differently than most uranium, which is uranium-238. Uranium-235 decomposes through a beta decay into a new product. And we can use this information and our understanding of what a beta particle is to figure out the identity of the new particle. Now, a beta particle, you can write as a beta or an E, either one is fine. And the beta particle had a -1 in the bottom and a 0 in the top. So regardless of which one you use, you'd want to use one of those two symbols, and either way is fine. Uranium on the periodic table is number 92. So the uranium-235, we get the 92 from the periodic table. The 235 is what this number means. It's the mass number for uranium. So at this point, knowing this is our reactant, decay means that something's going to be a product. So we'd write one of these on the product side. And the only other thing we don't know then is our missing product particle. So in this problem, once again, uranium-235, the 235 is the mass number, the upper left number. The 92 came from the periodic table because uranium will always be 92, and 92 protons, always uranium. Beta decay, or beta emission, means that a beta particle is a product. So a beta particle, 0 minus 1 beta or 0 minus 1 E, either way is fine. And there's something else created, and that's what we're going to find in this problem. Any questions on what this means so far? Okay. So finding Z and A might look a little weird at first, but it's not as bad as you might think. Because again, on these reactions, the lower left numbers on the reactant side equal the lower left numbers on the product side. And the upper left numbers will balance too on both reactant and product side. And once we have this lower left number, we can use the periodic table to find what the symbol is for that element, what the X is. So 92 equals -1 plus Z. We can find out what that is. 235 equals 0 plus A. So that's pretty chill. A is just equal to 235. So the mass number of our species will be 235. And then 92 equals minus 1 plus z. So if we solve for z, we'll add 1 to both sides. So 92 plus 1 means this is going to be z is 93. And if you look on the periodic table, right next to uranium is Np, which is Neptunium. And Neptunium would be the missing element, that part that's decomposing into. So uranium-235 breaks down through beta decay into Neptunium-235. That's the jargon you would use with this kind of stuff. Beta decay or beta emission means that something's going to be a product. Now, what's really weird here is that notice how the 92 on the bottom went to a 93. So it feels kind of like we're making a new product, all right? We're making a new proton. But this is an example of one of the main reactions in some of these problems, is that it's a neutron in uranium-235 which is breaking down. And that neutron is turning into an electron or a beta particle, as well as a proton. Now, we talked about at the very beginning of the section how protons were a little bit less massive than neutrons. And roughly, a proton plus an electron is the mass of a neutron. So this reaction, this inner reaction, if you will, is actually one of the neutrons breaking down into a proton and an electron. And this is why electrons usually get 0, -1 numbers, because -1 plus 1 is 0, 1 plus 0 is 1. This is the way that nuclear chemists show how a neutron is basically a proton plus an electron inside. And in these high energy reactants, this is something that happens sometimes. Beta decay usually involves then a new proton, and you'll see it by an increase in the proton number, which is very, very weird compared to everything else we've ever looked at up to this point. Like if we had a carbon, it stayed a carbon. If we had a magnesium, it stayed magnesium. But here, we've got a uranium, all of a sudden it's turning into neptunium. Welcome to the world of nuclear chemistry. Any questions? So here's an example of another kind of reaction, but same idea, all right? This is another reaction that uranium-235 undergoes. Uranium-235 is pretty reactive. So making the neptunium was one pathway. This is another pathway. And this reaction is making a thorium-231. Thorium used to be used in lamps that miners used and stuff for a while. But anyway, this is a thorium-231. Thorium, named after Thor, by the way. Oh, yeah, Marvel. Okay, prop that back on. Thorium, number 90, all right? We can figure out what the missing piece is in this reaction, just like we did with the last one. And again, what you want to do is, first of all, find the numbers that go along with it, and then we can figure out which of these is a possibility. So if 92 equals 90 plus z, what is z going to equal? 2, that's right. So the bottom number here will be 2. Now on the top numbers, 235 equals 231 plus a. So what is a going to be? 4, that's right. Does anybody remember what particle had a lower number 2 and an upper number 4?
Oh.
Alpha, well done, Gabe. Yeah, alpha, you could write helium, that would be fine too. It's an alpha particle. So this particular version, good, is, I was like, what did I not find? Okay. Anyway, this particular version, this is an alpha emission, all right? An alpha particle is being kicked out of the thorium, or uranium, excuse me, and you end up with the thorium. Cool. Any questions? So emission and decay, you'll hear those terms a lot, and those always mean that some kind of product particle is being created. So we've seen an alpha emission or an alpha decay. We saw a beta particle emission or a beta decay. They're both used the same kind of thing. You can see other types of particles though. Here's positrons, my good old antimatter, like anti-electron. Polonium-207 undergoes positron emission to make bismuth-207. So again, all you need to know is, besides thinking about the science fiction, which blows my mind, but anyway, lower left-hand numbers balanced on both sides, upper left-hand numbers balanced on both sides. You can figure out what the missing piece is, positron. So this one kicks out a positron. Now, once in a while you'll hear about capture, all right? Unlike emission and decay, which means that's going to be a product, capture means that it's going to be a reactant. So a neutron capture reaction would have a neutron as a reactant. This is an example of a fluorine-19 undergoing neutron capture to become fluorine-20. Still fluorine because the atomic numbers haven't changed, 9 plus 0 equals 9, but the mass numbers have changed. 19 plus 1 is equal to 20, all right? There's lots of examples of these particles out there. There's lots of examples of decaying emission, capture. For your purpose, just remember this is like capture, decay, emission, CDE. Capture, reactant, emission and decay are products, all right? So it could be, I don't know, a chromium decay, and you would have a chromium particle as a product. Whatever it says, that's going to be a product. On the other hand, if it's a capture, then it's going to be a reactant molecule. Any questions on that? Okay. Let's talk about antimatter just a little bit more. It's really storming outside. That thing is going back and forth. If it bothers you, I could lock it, but if it doesn't bother you, I'll just keep it there. Anyway, antimatter. Woohoo! Not just from Star Trek. All right. So I get to talk about Star Trek and antimatter. Okay, back on. Paul Dirac was the first person to propose antimatter. All right, and Dirac was one that did the MS spin quantum number and quantum mechanics. If you remember, if you don't, it's no problem. But anyway, 1928 was the first time that it was proposed that you could have regular matter but an opposite charge. And in science fiction, this is huge. They're always talking about antimatter this and antimatter that. This is real antimatter, and it's interesting because antimatter is becoming more and more of something that's legitimate to study. Now, if you have matter and antimatter come together, it's basically big explosion. But in this world, how you would talk about, instead of being juvenile and using bad sound effects, you would somehow probably represent lots of energy being created. So this is an example of taking a regular electron and an anti-electron. An anti-electron is again a positron. And if you add these together, notice what happens. -1 plus 1, 0. And 0 plus 0, 0. Now, two particles coming together means you're going to have two gamma rays. But this is pure energy. So instead of going, all right, this is what really happens, man. They annihilate each other. They undergo what's called an annihilation reaction. So if you had a proton and an antiproton, sound effect's not necessary, you get the idea of gamma rays. You can have regular hydrogen and anti-hydrogen come together. And there's lots of cool science fiction things, but there's also lots of science now. Because one day they're going to hopefully need ways to get from our planet to other planets, and this would be one source of energy. If you could somehow control the antimatter-matter interactions, man, you'd have a lot of energy. So this is what they're thinking about. Now, this example right here with regular electrons and anti-electrons is actually used up at OHSU. They have positron emission tomography, PET, which is a type of analysis. They can look at tissues and stuff that does use anti-electrons, these positrons. So again, this is no longer just for Star Trek geeks and stuff, and yeah, but on the other hand, there's some really cool kind of uses for it. This is an example of what's called a neutrino. Neutrinos are another type of particle that gets kicked out of nuclear reactions. And neutrinos can also react with antineutrinos. Sometimes antiparticles get a little bar over the top of it. And again, the effect is the same. Lots of energy in these annihilation reactions. You just make them two gammas. Pauli, the Pauli exclusion principle, was the first one to propose neutrinos. when you get into these particles a lot, sometimes little neutrinos get kicked out to keep everything balanced up. So just realize that antimatter is no longer just for science fiction, all right? These are real particles, and it's actually an active area that people are studying. They hope to get some energy out of it. And when antimatter and regular matter come together, then there's lots of energy released. In science fiction, especially Star Trek, when matter and antimatter came together, a lot of energy. Same idea here. This is just the science version, if you will. So, questions on that? Now, earlier we saw a uranium-235, and we saw a couple different ways that it breaks down. And so a decay scheme is really important when it comes to nuclear science to try and predict how these things are going to break down. And this is the decay scheme, i.e. how uranium-238 breaks down. Now, uranium-238 initially goes to thorium. And then thorium goes through a couple steps until you get to uranium-234. And then that breaks down to thorium, to radium, to radon, polonium, lead, et cetera, et cetera, et cetera. And then down here at the very bottom is the stable isotope, all right? So all these other little black dots here are considered more or less to be unstable until you get down to the very end. And if you have then some radioactive uranium and you want to know how it gets to something stable, this is the kind of analysis you need. Now, if you look, these gaps oftentimes have a mass number change of 4. So 238 to 234 would be 4. And those are all alpha decays. Alpha decays are pretty common for the heaviest ones. On the other hand, here's 90 to 91 to 92 essentially. That's going to be some kind of beta thing going on, some kind of beta particle where a neutron is breaking down. So we're not talking here about how long it takes, we're just seeing like how these things break up. And using this kind of thing, you can then predict, aha, well, this is going to be an alpha decay, this is a beta decay, stuff like that. They can be really helpful if you're looking at trying to get rid of nuclear waste and stuff like that. Now, another player in all this that you see sometimes is what's called a metastable nuclei. And sometimes you can like supercharge an atom. It doesn't transform to a different atom, but the neutrons and protons become super agitated, all right? And so a metastable nuclei is something that happens. It happens a lot with gamma rays. Now, the classic example of a metastable nuclei is with technetium. And technetium is also something that's used sometimes up at OHSU for analyzing different substances. If you see a little m next to the mass number, that's what means it's metastable. Now, normally technetium has 43 protons, and 99 minus 43, it must be about 55 neutrons or so. And 56, I guess, actually, sorry. But anyway, those protons and neutrons are usually distributed really well. So protons are kind of mixed in with the neutrons. But in a metastable state, all of a sudden you have most of the protons, if you will, on the left, and the neutrons are on the right. So it's metastable, it's an unstable mix. Protons don't like to be next to protons generally. They like to have neutrons in between to kind of separate them. So metastable is like an unstable configuration of protons and neutrons. And after a while, the metastable state relaxes. It emits out that extra energy, which is usually gamma, and you end up with regular technetium without the M. So if you see a little M next to the mass number, that's this metastable thing. And all it means is that after some amount of time, usually pretty fast, it kicks out a gamma ray, and then you have the non-M version or the regular version of the element kicked around. So if you see that M, that just means it's going to break down into a gamma ray. It's going to be reacting. And again, medical imaging actually uses this technetium-99M, this unstable version of the isotope. And again, it will break down to its normal version plus a gamma ray after a while. I've seen some examples of mercury with some of the mercury compounds that are metastable, but technetium is the main one that you see usually. Questions on that? Okay. So now, thinking about the stability of the nuclei is definitely something that's pretty important. Because if you've got a gamma emitter running around in your house, you don't want it there. You want to know how long it's going to take and stuff to get rid of. On the other hand, like Caleb brought up, there are good uses for some of these things. It might be you want this stable, say the unstable version, to stick around for a while. So in order to understand when things are stable and unstable, we need to now take a little bit of a side tour and talk about the forces of nature. All right? Now, according to science, all right, there are 4 forces of nature that hold everything together. So if you look at all the things around us, all right, from this building to our bodies and everything else in between, there are 4 forces that make all this possible. And the first of the forces is gravity, or the gravitational force. And gravity, of course, keeps us on the Earth. It keeps the Earth rotating around the sun, stuff like that. Pretty important. However, when gravity is compared to the other forces we're going to talk about, first of all, it's a relatively weak force, all right? If you compare the forces, strength to strength, gravity is actually one of the weaker ones, which is kind of weird because obviously as I jump, I'm not like floating away to the moon or anything, all right? It seems a little weird, but compared to the other forces, gravity is a weaker force. And gravity is also a relatively long-acting force, long distances. So it does hold our planet around the sun, and our solar system is in the galaxy, the Milky Way galaxy, stuff like that. Gravity is a long-range force, all right? And it is important, but it's a lot different than the other forces we're going to talk about here soon. Now, the next force is one that you probably haven't heard of, or maybe you have, and it's not one we're going to talk about a lot in this class, and it's called the weak nuclear force. And just like gravity, it's a pretty small distance kind of force, pretty short range, all right? It only works when the things are very, very close, closer than like protons and electrons even. Like I said, we're not going to talk about weak nuclear here too much, but it is responsible for beta decay. So if you see a beta particle being kicked out, it's usually the result of the weak nuclear force. The 2 forces, though, that we're going to focus on a lot in this conversation are electromagnetic. And man, this is the heart of chemistry. These are the positives and the negatives. These are the ions attracting to other ions, stuff like that. This is a pretty important force. Now, EM force, which I've also called Coulombic forces and stuff like that, this is the positive, negative, the ionic forces and covalent and your polar, all that kind of stuff. Now, electromagnetic force is considered to be a relatively long-range force compared to what we'll talk about next. It's not as long as gravity, but it is a relatively long range. And most of chemistry is really involved in the EM force, all right? Keeps electrons around the nucleus. Check this number out. They claim it's about 10 to the 36 times more powerful than gravity, all right? So when it comes to gravity versus positive negative, the positive negative is considered to be a stronger force. Now, it's not by any means as long range as gravity. All right, gravity, like I said, holds solar systems and the whole galaxies together. But EM is pretty important for keeping the atoms connected to each other. And it keeps the different polyatomic ions in an ionic bond, if you've got them, stuff like that. Most of Chem 221 and Chem 222, we've basically been focusing on the electromagnetic force and how it applies to chemistry, all right? The positives, negatives. We talked about gravity a little bit, like when the stuff goes up the barometer, when mercury starts falling, but most of chemistry has been EM so far. But the 4th one is a new one, and that's going to be really important in this section. And it's called the strong nuclear force, all right? Now, the strong nuclear force is even stronger than the EM force. It's about 1,000,000 times stronger, they feel. It's a very, very short-range force, 10 to the minus 15 meters. Now, atoms are roughly an angstrom in size, which would be 10 to the minus 10 meters. So this is much smaller even than the atom. This force, though, is involved in the nucleus, all right? And the EM force is what helps to keep the protons from attacking each other. Because remember, positive protons next to positive protons, they want to repel all the time. Like charges repel, opposites attract. So to keep the protons from basically making the atom break down, because positives and positives don't get along, the strong helps keep the neutrons neutral, kind of in between. And people a lot of times think that the glue that holds the nucleus together is the strong nuclear force, all right? It overpowers the EM positive repulsion that exists in the nucleus all the time. So while the atom overall, positives, negatives, that's the EM electromagnetic force, this strong nuclear is what keeps the nucleus in check, keeps it stable, all right? And as long as you have a relatively short range going on, the strong nuclear is able to overpower the M and keep the atom stable. So, when I think about what keeps our atoms together, the nucleus is powered essentially by the strong nuclear force, all right? It keeps all the protons happy. But the overall atom, we would say those positives and negatives, we're back to the Coulombic or EM forces kind of keeping them together. Any questions? Okay. So this is really interesting because all the things that we know, all right, planets, you know, bugs on the water, everything, something to do with one of these four forces. And that's kind of cool, a little bit. People in physics have combined the last three forces together, but they haven't done a very good job understanding gravity yet, which is also something. But now we're definitely into physics, and I want to keep it up with chemistry. So knowing about these forces, especially the strong nuclear and the EM, we can start to talk about when things are stable in an atom, all right? And nuclei become unstable. They start to break down because that EM force, those positive protons start to not like being next to each other. And when that starts to kick in, that will break your atom down. It'll break it into smaller atoms, all right? Now, magnetic dilution is the fancy term used to keep neutrons in the nucleus, and it keeps those protons stabilized from each other. Keeps them a little bit further apart. Hey, you sit there and you sit there, and now you be friends. All right, that's kind of what a neutron does, and that's a result of this strong nuclear force. And it does help to a point, but after a while, even these things begin to break down. So when scientists look at the periodic table, up to calcium, the most stable isotopes will have equal number of protons and neutrons. There are a couple of exceptions, hydrogen being the main one. But if you go look at all the elements up to calcium, basically protons and neutrons are the same. So as an example, let's look at number 12 right there, magnesium. You can see that the average mass, 24. So the average mass of the magnesium that would be about 24 for the mass number. That would be 12 neutrons and 12 protons. So roughly, up to calcium, that's kind of the rule. Protons and neutrons should be about equal. Now, past calcium, but up to bismuth or so, or lead even in this case, protons will always be less than neutrons in the most stable form. Because as the atoms start getting bigger, now the protons start getting a little more angry with each other. So you need more neutrons to kind of keep everything spread out. So up to lead, some people say bismuth, but I think it's lead. Up to lead, the most stable nuclei will have more neutrons than protons. And those neutrons just help to dilute that positive repulsion that happens in the nucleus. It keeps the strong nuclear force an active player. But the thing is that once you get past lead, all atoms are unstable, all isotopes. And arguably, they're all radioactive in some form. So this is another thing. If you look at the periodic table, our periodic tables in this room, the periodic table, the atomic numbers, the mass number, atomic weights that are surrounded by parentheses are the unstable ones. And you can see that a lot of them past lead, which is number 82, right there, have those parentheses around them, astatine, polonium, etc. Now, not all of them do. So like here's bismuth, here's uranium, which doesn't. But a lot of people feel that even those will break down. So we need to talk a little bit about more what stability means. Like, what is stability in terms of an atom, and what does it mean in terms of us being human beings on Earth for 70-ish years? So we'll talk a little bit more about when things are stable and unstable. But when scientists collectively look, all the atoms up to calcium, the most stable isotope generally, protons and neutrons are equal. Past calcium but up to lead, then these stable isotopes will have more neutrons than they have protons. And arguably, past lead, everything is unstable and radioactive. Questions on that? So this is one of the coolest concepts of the whole chemistry series. This is a graph, and there's different versions of it, but this particular one has neutrons, number of neutrons on the y-axis, and number of protons on the x-axis. And if you look at this graph, there's like black dots and red dots. The black dots are the stable atoms, and the red dots are the radioactive isotopes. This line right here would be a slope of 1. So that means in this graph that protons and neutrons would be the same. So notice that if this is where protons and neutrons are the same, the graph starts going more up like this. And that just means that around here you start having more neutrons than you have protons. But also if you look, the black dots kind of give out after a while. And this doesn't show as many as I'd like, but after a while, the red dots totally surround the black dots. So people that are very imaginative in this field have called the black dots a peninsula of stability. And a peninsula of stability just lists all of the isotopes of the atoms which are stable. They won't break down by alpha decay or beta particles and stuff like that. And the red dots, which do surround all the black dots, although it's not super clear there, the red dots they call the sea of instability, all right? The sea of instability just means you're in different atoms now, which are radioactive. They're going to break up. So this is a classic thing from nuclear science, the peninsula of stability in the sea of instability. And they talk about then the stable atoms, the black dots, surrounded by the unstable ones, the radioactive ones, the sea of instability. So people get really creative with this, and you can agree with it or not. It's up to you. Any questions? Here's a more scenic graphic thing, and you can tell there's like sea serpents in the sea of instability. You can imagine people's creativity goes pretty crazy. But anyway, a peninsula is literally like a part of land that juts out into the sea. So in this context, the sea of stability are just the ones that are very stable. And around that, the red dots were the island or the sea of instability. Now, scientists with more background in this than I have predicted that there's going to be islands of stability in the sea of instability. And what that means is that somewhere past our little peninsula that we're used to on the planet Earth, there's going to be islands out there with some combinations, here's one possible combination, of protons and neutrons that's going to create stable isotopes. And I find that super exciting because one day our periodic table might have elements with like 200 protons. Woohoo! Right now we're up to 118, which is under radon. The theory is that maybe one day they're going to be able to find some stable isotopes that are way past our area right now. And they've done some calculations on this and stuff like that. We'll talk about Seaborg later. He's a main player in this area. Ken Moody was one of his graduate students, and they did a PBS study on this, a NOVA thing about this island of stability and stuff like that that are possible. Anyway, questions? So here's another thing and stuff like that. If you have to predict how an atom will break down, all right, there's going to be different combinations of things that are possible. This is another graph, protons versus neutrons. And you can imagine in the middle here would be like the island, the peninsula of stability. But generally speaking, more neutron-rich things, they will break down, their neutrons will break down into that beta decay. So you'll see the rising of the atomic number. On the other hand, super big elements will usually break down generally by alpha decay. They want to become more like lead, the last stable one that's around. And neutron poor ones will be these positron emissions. So I would never hold you to this because there's a million different variations. But generally speaking, if the atom has high neutron to proton ratio, then they'll undergo beta decay. So if we knew that uranium-235 was a high neutron to proton ratio, we would predict that most often it breaks down into a beta decay. Now that's not all the time the case, and there's a lot that goes on with these kind of discussions. But if I said that uranium-235 breaks down through a beta particle, then you can predict what the products were. If you have a low neutron to proton ratio, then positron emission or electron capture happens, positron being more predicted. Now, nitrogen is usually nitrogen-14. And again, to figure that out, if you don't know, you can look on the periodic table and the N number there is 14.0067. So 14 is the most common version of nitrogen. So nitrogen-13, all right, would have less neutrons than protons relative to nitrogen-14. And if you have one of those weird things, then it usually undergoes positron emissions. Again, I would tell you if this was undergoing positron emission, but they generally feel that if you have a low neutron to proton ratio, this is what happens. And then generally speaking, the heavier ones, if you don't know, most of them undergo alpha decay. So in this case, this is a radium-226 I showed earlier. It undergoes alpha decay to make it to a radon. These are general trends, and I would never ask you like if some isotope has this, this, or this to it. I think that's more fun than we need right now. But at least you can see how scientists think about how the atoms are decaying, which is kind of crazy to think about. Questions? Okay. You can figure out the energy of a transformation of a nucleus using this process. And most of the stuff in this section doesn't have a lot of math. This is the one section where there's a little bit of math, but honestly it's not as much as the last couple chapters have had. If you make an atom, all right, you're going to get some energy out because atoms form, thankfully, and that's what makes human beings and caffeine and all these kind of things. So you can actually figure it out. Now remember that the strong and weak forces are stronger than the EM force or gravity. So sometimes by comparing the energies to make an atom, you can make predictions as to which one has stronger strong forces or weaker strong forces. So binding energy, which is called E sub B, is a way that people will try to estimate how much force comes through for a specific atom. And binding energy has a really weird definition that probably doesn't sound right at first, but I'll show you what it means. The binding energy, E sub B, it's the negative of the energy change if you take a nucleus and you form it from individual protons and neutrons. So if we take, say we're curious about carbon-12. All right, well, carbon-12 comes from 6 protons and 6 neutrons. There'll be so much energy to take the protons and neutrons to make carbon-12. And it'll be a negative number because carbon likes to form. E sub B would be the opposite of that number. And I'll show you why it's the opposite here in a little bit. So what we'll do now is we'll do an example of a binding energy calculation. And we'll then talk about what it means. And the ramifications are pretty crazy. Questions so far? All right. So let's figure out the binding energy, which is E sub B, for making hydrogen-2. Now hydrogen-2 is an isotope of hydrogen. Hydrogen has 3 main isotopes. Normal hydrogen is just 1 proton with no neutrons. But deuterium, which is hydrogen-2, has 1 proton and 1 neutron. So this is what we're going to look at in this problem. It's taking a raw proton and a raw neutron and combining them to make deuterium, make hydrogen-2. And we'll think about the energy required to do it, and then we'll think about what the binding energy means. Now, to use this equation, what we're going to do first of all is look at the individual masses. And if you look back at Chem 221, or Google these things, a proton plus a neutron, the total mass comes out to be this number, 2.016475. And what's kind of disturbing, but kind of interesting too, is if you do the same thing and you look up deuterium, deuterium's mass, 2.01410. And oh my gosh, as a chemist, this makes me very nervous. Because since Chem 221, I've been harping on you how you gotta have the balanced reaction. Mass in equals mass out, all that kind of stuff. And we balanced equations and did all that jazz. Well, here I'm showing an example where the mass that goes in is greater than the mass that comes out. All right? Whoa. And what the heck's going on here? Because there's a mass loss. All right, your delta M, if you will, which is final minus initial. Your final minus initial, or the change of mass, is negative. Mass is not conserved. Now, of all the things that make this section unique relative to the other chapters we've looked at, Chem 221, Chem 222, this is my number one thing. Because this is like, oh my gosh, mass is not conserved. What the heck, man? Because balancing reactions, making sure the stoichiometries, diatomics versus regular versions, etc., that's been such a big part of our world. And here, now in this nuclear reaction, we're seeing that the raw proton and neutron to make hydrogen-2, mass is not the same, all right? So in order to get around this and figure out what the heck's going on, we're going to revisit one of the great scientists from Chem 221. I see people still writing down, so give me just a second. There were a lot of great scientists in Chem 221. But one of the greatest scientists of all, we'll pop his name up here in a little bit. Okay, so this is a mass lost upon making deuterium. 1 proton plus 1 neutron making deuterium. We have lost mass, but that's actually okay thanks to Einstein. Now, Einstein, what we did in Chem 221 is we talked about the photoelectric effect. Light goes on metal and electrons are kicked out. That was a weird thing unto itself. But the thing that Einstein's also known a lot for is E equals mc squared. And that's what they call the energy to mass conversion sometimes. And this is another big part of Einstein's world. And we're going to use this problem because that lost mass is being turned into energy. Now, how this works, delta E equals delta M times c squared. C is the speed of light, 2.998 times 10 to the 8th meters per second. And that's the speed of light squared. And if you multiply that by the kilograms per mole version. Now, in the last slide, it was grams per mole because that's what chemists usually use. But a joule is a kilogram meter squared per second squared. So we've got to turn grams per mole into kilograms per mole. And if you do that, you end up with this number, minus 2.15 times 10 to the 11th joules per mole. This is the energy released upon making 1 mole of deuterium. Is this a lot of energy released or just a little energy released? A lot, you bet. In some of the stuff we've done so far, like acids and bases, all right, or sodium, metal, and water, the energies were 10 to the 6, maybe, joules per mole, or 10 to the third kilojoules. That was a common energy transformation. But making deuterium orders of magnitude bigger than those kind of interactions. This number is big and negative, exothermic, and it just shows that atoms want to form, all right? That's the reason right there, that big negative number, that atoms form at all. So it's a huge amount of energy making deuterium, all right? Not just the little energy, not just the things we've looked at so far. This is orders of magnitude larger. It's very negative exothermic. And again, this just justifies why we have atoms, all right? Why atoms and then make molecules and stuff like that is a whole other thing. Questions on that? Okay, now, binding energy is the opposite of this energy transformation. So if you take the opposite of this number, it of course becomes positive. And I'm also going to turn joules per mole, this means per mole once again, I'm going to turn joules per mole into kilojoules per mole. So the binding energy for this reaction then, making deuterium, 2.15 times 10 to the 8th kilojoules per mole. This is the energy that supposedly is saved through stabilization, through nuclear stability of the neutrons and the strong nuclear force, stuff like that. And again, what this does to a scientist, it helps them justify why atoms form at all, right? If E sub B was 0 or even negative, then there'd be no reason for the atoms to form. But because it's a big positive number, that just shows that, yeah, scientists really want to happen. Well, atoms really want to form, excuse me. So in this, we use Einstein's equation, E equals mc squared. We turn grams per mole into kilograms per mole to make the units come out to be joules. That's the one weird thing. Then we went joules per mole to kilojoules per mole, turned the negative into a positive, and we'll see why here in a little bit. This is how we got the binding energy value. Okay. Now, one final thing, and then we'll take a break. This is the binding energy in kilojoules per mole. Sometimes people will talk about the binding energy per nucleon. Nucleons are just the number of subatomic particles in the isotope. So deuterium has 1 proton and 1 neutron, or 2 nucleons, number of pieces in the nucleus. So the energy here, this 1.08 times 10 to the 8th, that's the energy saved per nucleon in deuterium. And again, it's quite large. There's a lot of energy saved. This is what they feel the strong force does to keep the nucleus together. Quite a bit of energy. Any questions? Okay. This stuff has huge implications, but we'll talk about that after the break. So it's about 10:56. About 11:05, we'll come, or 11:05, 11:01 or so, come back and we'll see what this binding energy actually means. And it's another one of those blow your mind.